Hi everyone, welcome back to our channel. I hope you and your family members are doing good because that is the most important thing. And for rest, we are here to talk. So we were following our pattern-wise DSA sheet. In this, we were doing 3 topics and today we will solve problem from DFS pattern. So the next problem from this pattern is subtree of another tree. So let's read the problem statement. It says we will be given the root and subroot. We have to return true only if there is a subtree of root with the same structure and node values of subroot, or else we have to return false. It means you can understand like this ki we will be given the tree, for that we have root, and we have been given the smaller tree and for that we have a subroot. So we have to check if subroot is a part of root or not. So if it is a part, as you can see, subroot 4 matches with 4. If the node matches, then all of its children should also match along with the values. So can I say this subroot and this subroot, when we find any root in this actual bigger tree matches with the subroot, then we have to go for the left check and right check. And now it's nothing but the same tree check that we already discussed in our previous video. I'll attach the link somewhere here. We have discussed both with BFS and DFS approach. So I am assuming you all know that how to do the same tree check. Now let's move forward. So let's move on to the constraint part. It says the number of nodes can be from 1 to 2000 in the bigger tree, which is root, and the number of nodes in the subroot can vary from 1 to 1000, means almost half of the size of the tree. It means for sure our subroot either lies in the left part of the main tree or right part of the main tree. How? Because it says na the size of subroot will be 1000, which is almost half than the root, and that indicates if the size of root and subroot are same, means the root and subroot both are actually same, or else the subroot might exist either in the left part of the root or in the right part. Also, the values of root and subroot ranges from minus 10,000 to plus 10,000. Although we don't have to worry about the values. Why? Because here we are not multiplying or adding the values. So we don't need to worry about the integer overflow. So here we are having root and subroot. First, the very first approach is our root matches with the subroot. If it matches, then we have to go for their left and right checks together. But in this case, 3 and 4 does not match. So our task is to check in the root's left part or root's right part. So in root's left part, we will match 4. Is the 4 matching? Yes. So notice this very carefully ki when 3 and 4 does not match, we move on to 3's left. Correct? Means we change the node from root to root dot left, but subroot remains same. Subroot will not move until their node matches. Okay. So now here 4 matches. Yes. So now we have to call the same tree check where we have to send the root and we have to send the subroot as well. So here the root matches. Yes. So now we have to move towards the left, means root dot left. Along with that, subroot dot left will also move. Why? Because this root and this root matches. Then if they are same tree or not, for that we have to match their left child with their left child. Now if 1 matches, now we have to move for the right child. Correct? So as you can see, the right child 4 does not matches with 2. Hence, from wherever we started, this does not match. So from here only we went on to the same tree check, right? So as we have returned, so now our task is to check this subroot with this left child of 4, which is 1. Here it does not match. Now this subroot with the right. Here 4 matches. Yes. So again we have to call the same tree check. Now the left child will match with left child. Right child will match with right child. Now is this same? Yes. So if it is the same tree, we have to return true. We have to return true. Now, do you think we should go in the right side to check the subroot when we have already found this subroot in our left part? No, right? So hence we have to return true if any of these left side or right side returns true for subroot check. Now let's think about the base case. What if root becomes null? What if root becomes null but subroot is like this? So should we return true or false? Means our task is to find this tree in a tree which does not exist. So we should return false, right? But vice versa, it should be true. Why? Because I am saying the true exists, but subroot says null. So is this null a part of root or tree? Yes, of course. Null means anywhere you can say null, yes. Hence, if root is null but subroot exists, return false. But if root exists, subroot does not exist, return true. So what is the first base case? Ki in is subtree function where we are sending our root and we are sending our subroot. Correct? Now, if root becomes null, return false. Now you might be thinking ki how the root can be null when the question itself says ki minimum one number of node will be there. Because we are applying the DFS approach. First we will try to match this 3 with the 4. If it does not match, then what we decided ki we will move root dot left and move root dot right, but subroot will be as it is. Suppose this does not exist. So in this case 4 matches, yes. 1 matches, yes, but 2 does not match with 4. So hence we will move for the next children, means 4's left, which is 1. Now we'll try to match this 4 with the 4. Yes, it matches, but its left child and right child does not exist. So this is also not a part of root, means this subroot tree is not a part of root. Now we'll go back. Now we'll try to match with 5. No, it does not match. So at a time we will go towards the null na. So here also you saw na, we went on null, but subroot exists. So we are writing the base case for that recursive call and not considering what if initially root is null. Okay. So now what is our task? Ki first we check the base case. Yes, root to exist. Root exist. Now what is our task? Is if this and this matches. So basically we will try to match the same tree check with root this and subroot this. So we will write a same tree check function and this root and this subroot value does not match. So that same tree check function will itself return false to us. So what is our task? First task is ki check with this root and this subroot if it returns true or not. So what we say ki if, let's say, same tree check function, there we will send root and there we will send subroot. If that function returns true, then we will return true then and there. Correct? What we said, suppose instead of this we have a root with 4, 1 and 2. So this root matches with the subroot. So then and there return true na. Why you want to go towards the left side and right side to check? Correct? So if same tree with the root itself returns true, then and there return true. No need to go towards the left and right side. Correct? But here the root and subroot does not match. Then what is our task? Our task is to go towards the left side, go towards the right side, and whatever returns true, either of these, then we will return true. Correct? So what we will say? Ki return true if same tree check. Now in this we will move just root dot left, means go towards left side child. Why? Because subroot and root does not match. Then only we are going towards the left side. So when we are going towards the left side, only root dot left and root dot right child will move. Subroot will remain same. Correct? Now for this we have to do the OR operation and we have to add same tree check with root dot right child and subroot. Can I say that? Done. That's it. Now what we will do in the same tree check, that we have already discussed. So for same tree check, considering now we have to check if this tree and this tree are same or not. So first base case was ki if both are null, means root is also null and subroot is also null, are these same tree? Yes. So return true. Now if this is null but this is not null, return false. Similarly, if this is not null but subroot is null, return false. So if both are null, return true. Can we write in the same tree check for you all again? Okay. So let's say same tree. In same tree we will have root and we will have subroot. Correct? So here what we did, the base case, ki if our root is also null, similarly and means both are null and subroot is also null. So if both are null, return true. Return true means both are on the left or right side of the leaf node. Can I say that? Now after this we will write ki what if any one is null. So if root is null or subroot is null. Why we are checking this? Because what if any, like after checking ki both are not null, why we are checking? Because after checking both are null, it says no, both are not null. Now if this if case runs, means either root is null or subroot is null. So in that case we have to return false, because it means ki any one of these exist. Okay. Now if this if case also not run and this if case also not runs, it means for sure both root exist. So if both root exist, what if their value does not match? Suppose here only we called for same tree check, right? So this 3 does not match with 4. So do you think we should go towards the left side to check or right side to check? Considering we just have to check if this tree and this tree are same or not, because we are writing the same tree check function and not subtree. Okay, so if we are writing the same tree check function, if the root and subroot does not match, it will not make sense to check for their children's. Okay, so if both tree exist, we have to check ki if root dot value not matches with subroot dot value, it means parents are not matching. How can the children match? And hence it is not a same tree. Or else if it matches, in this case so it does not match, so it will return false to this. Now we will go on to same tree for left side and for right side. Because we have written the same tree for left side called first, so this will get called first. So now this will be root and this will be subroot, correct? So we will check, are these null? Where we will check? In the same tree. So it will say no, these are not null. Now it will, this second if case will check, is any one of it null? No, it's not null. Now we'll check, are their values does not match? No, their values matches. Now it's time to go towards the left child and go towards the right child to check. So we will return true only when the same tree check function with root dot left and subroot dot left returns true. Along with that, and same tree function for root dot right and subroot dot right also returns true. Why we said this? Why we said this? See, here 1 1 will say it is matching. Yes, but we cannot return true, because if complete same tree matches, then this should also be same tree. Okay, so we have to check if this 4 and 2 matches, it will say no. So it means from 4's left side so we got true, but from 4's right side we got false. So and operation will say no, we have not got, correct? So this was for this tree and subtree check. Can I say that? So this will like 4 will return false, correct? Now what we will do? We'll go towards 4's left side, means we will try to match this subtree with this subtree. Again it will say no, it's not matching because the value of the parent itself does not match. Now we'll go towards the right side. We'll try to match this subtree with this subtree. Again 4 4 matches, yes. Left side child matches, yes. Right side child matches, yes. So in this case we will return true. So this return true will get returned to this and will get returned to final true. Okay, talking about the time complexity, as you can see we are trying to match every node, correct, then their children's, and once it returns false we are getting outside. So don't you think for every root we are trying to match the subroot's whole children? Similarly we are again starting from this 4 to match this, but we matched this, but because 4 and 2 does not match, so we return back. Now we tried matching with this node with the whole root. Now here again with this node with the whole root. So isn't it n square? Here you can say we are the only matching with this one node, but consider the worst case. What if all nodes are 1 1 1 1 1 1 1? Similarly it has 1 1 and last 2. So you will try to match this one, then this one, then this 2 does not match, so you will return back. Again you will start from this one, correct, 1 1 2, suppose this one. Again you will match this one, then this one, then this 1 and 2 does not match, you will come outside. So in the worst case scenario, you will try to match all the nodes of the subroot in every subroots possible for the main tree. So hence in this case the time complexity will be n square and the space complexity will be, can I say, the DFS call as it is a balanced binary tree. If it is a balanced binary tree, I can say the space complexity will be logarithmic of n, which is nothing but height of the tree, correct? And if it is a skewed tree, then the space complexity will be O of n, where n is the number of nodes. Okay, if you are following our playlist, you would have understood this line till now. Now this condition is a subtree is also using the logarithmic of n space complexity. Similarly, is the same tree is also a DFS function and it is also using the logarithmic of n space complexity. So in total, 2 times logarithmic of n space complexity if they are balanced binary tree. If they are skewed, then 2 n space complexity. Okay, so this was your DFS subtree check. Now the question is, can we do this same thing with BFS also? Yes, we can do, but DFS is more preferable because after every root check we are going towards left side and right side, and if you want to do the same with BFS, then you have to store the root also and their level also by making the pair inside the Q data structure, which makes it little messy, although the time and space complexity will be similar only. In BFS, the space complexity will be exactly 2n because there we will be using Q data structures. But still, if you have any doubt, the same tree check we have already done in our previous video, both with BFS and DFS. So you can definitely check it out there, and you can try submitting this code using BFS on your own. And if you have any doubt, do let me know in the comment section. So if you understood this, let's try to write this code in the editor. So here is the code what we have discussed. First, for the is subtree check, the base case if root is null and subtree exists. First, the base case if root is null and the subroot exists, means we should return false then and there. Or else first we have to check with the root with the subroot. If this returns true, no need to go in the left check and right check. But if root does not matches with the subroot, then our task is to go in the left side and go in the right side, and whatever returns true, we have to return true with the OR condition. Now this is the same tree check function where we have already discussed about how to do the same tree check in our previous video. I hope you all know that. So this was your Java code. Let's try to run the code and we will submit this. As you can see, the time, like the number of nodes can go till 2000. So the time complexity for this code is n square. 2000 means 2 into 10 power 3. N square will become 4 into 10 power 6. Correct? So this was your Java code. Here is your C++ code for the same logic, and here is your Python code for the same logic. If you understood this, do like the video and do let me know in the comment section that yes, you understood and submitted. Until then, you can go in the sheet and mark the next question also as done. So if you have any doubt, please let me know in the comment section, and I hope you will make your own notes so that you can revise it later also. So hoping that you all would have submitted this code on your own instead of just watching the video. Let's wrap up this video. I'll attach the sheet link and my social media link in the description. You can even share your progress on any social media by attaching or tagging our handles. That's it. Let's meet in another video with some more interesting questions, topics and patterns. And then keep learning. Take care of yourself and your family too.